Thank you, Tari. First, could you confirm you can hear me okay?
Yeah, I can hear you all.
Thank you. So first, thanks the opportunity to share the MISO's experience. Thanks for the opportunity to present here. So the intention of the presentation is to share MISO's experience to adopt the GFM performance and standard. So recently, we've been working on with the stakeholders to post the GFM, the battery storage, IBR battery storage performance requirement, and recently just finished the PAC meeting and post the white paper. So few things, key takeaways as a summary for this presentation. So first, the driver here, this energy transition poses a critical challenges to the system stability. In the MISO has performed a real study, which is a comprehensive engineering study to capture the renewable transformation that indicate a 13% energy penetration. At that point, we're gonna see we're gonna start seeing the weak grid or this local voltage oscillation. And here we understand the GFM technology is essential as the system stability approaches that inflection point. So MISO, with the stakeholders together, we developed the GFM requirements to capture the core capabilities. So here, want to emphasize the core capability, want to bring this in as a stage one. We don't want to add additional cost for our developer, our generator owner, to unlock this capability. So we are also working on the future developments to extend the GFM requirement so the battery storage GFM can provide more grid service. So the LERC white paper actually indicates the GFM BSS should be adopted, and the technology is available today. MISO, we have published post 2023 attribute roadmap that also indicate, I have the link in this slide as well, that indicates the concern of the voltage stability because of the increasing renewable penetration, and also indicates the benefit of the GFM controls to support the voltage stability, especially under the weak grid conditions, which are likely to increase in prevalence. And in our real study, we indicate this inflection point, 13% energy penetration that is likely to happen around 2030, that time frame. There's two links here. Will bring you to MISO's attributes roadmap, and also the white paper, the grid forming performance standard requirement. So this slide shows our MISO's stakeholder process and how we just a recap of our process to get and achieve the white paper standard posting. So in the year of 2024, the Q1, we provided the background of the GFM best specification practices. Want to bring our stakeholder in to understand why we want to do this and why this is important, and also what we're trying to do. In Q2, once we engage a large group of stakeholders' attention, we shared our outline of our proposed GFM-based requirements. In Q2 2024, we have shared our first white paper draft. In Q3, once we share the white paper, provide more background information, then in Q3, we propose the implementation plan, and here the final white paper draft. So here, this process mostly we plan to implement that in our generator interconnection process. So just provide a little background of the generator interconnection, since right now we have seen an increasing volume of generator interconnection request in MISO queue. And at the same time, in generator interconnection, that process, the key priority is very important. And also, all these developers, we want to provide as much certainty as possible to them at the beginning. Also, at the same time, we want them to provide as much support to our grid as well. So in the Q3, we shared the implementation plan, shared with stakeholder what interconnection request cycle will be affected, and also share the final white paper draft that include a specific technical requirement and also the required test as well. In 2024 Q4, we proposed a business practice manual changes for implementation. So the business practice manual, that's a term we use in MISO. I believe in other RTO, ISO, they use different names. Basically, business practice manual describe the business process of certain process. So this time, in this case, is regarding our generator interconnection process. Also, is the interpretation of our tariff. So just in summary, we propose the testing requirements will be applied starting with MISO generator interconnection 2023 cycle. And currently, our 2023 cycle is in our phase one. A little background here, for each DPP cycle, we have three phases. The first phase is preliminary, then we revised phase, and the final phase. Currently, 2023 cycle is in the phase one. So we propose that implement this cycle. So the stakeholder or the developer will have sufficient time to understand the technology and to engage the consulting group to provide to meet this requirement. And as I mentioned a little bit earlier, so the GFM requirement at this stage, we propose just to implement the core capability. So here shows just a big picture of how we see this GFM implementations. So in 2022, we propose just the standard, the requirement to address all IBRs, mostly is focusing on the write-through capabilities. And in 2024 GFM, which is basically the what I'm presenting today, our progress is focusing on the system strengths and frequency support. And we're expecting GFM can provide support to improve our system strengths, our frequency support. And as down the road, we're looking at the GFM capability. We're looking at the black start capability and islanded operation. That's the potential future capabilities to be explored as need to materialize. So just want to focus a little bit more on these core requirements. So in this time, we propose only to adopt the core requirements in 2024. The core capability do not require hardware oversizing. And these capabilities are enacted through the available software settings supported by all state-of-the-art battery energy storage systems. The core capability, including the voltage source behavior, frequency domain response, inertia response, surviving the last synchronous connection, weak grid operation, and system strength support, oscillating damping. And just want to add a little bit more here, the additional capabilities that including headroom energy buffer and current capacity above continuous rating and black start capability, power quality improvement. So the core capability, what I see here is already available in current battery storage energy system. And we consider this a low-hanging fruit and can provide benefit to our system. In the stakeholder process, we have confirmed, we open up for comments, we have confirmed this capability will not require any hardware oversizing. It's focusing on just the software change. So want to make sure there's no additional cost to apply on our interconnection customers. As we target to apply all these changes to our 2023 cycle, which is already ongoing, want to make sure that this document, this standard requirement is not adding any additional uncertainty to their generator interconnection request. At the same time, we explained this can prevent what benefit, what grid service, what grid support this GFM capability can provide to our system. Down the slides, there's a link to our white paper that including our literature review, the background information indicates what other RTO is doing, what other energy entity is doing, and what their standard, and also provide the GFM requirement, the speculations required, and also provide the detailed test process, what is required to test to verify the core capability, and what is considered pass, what is considered fail. And also we have specific requirement how to set up the test bed. The intention here is to make sure the process provides least uncertainty, least confusion, so our developer, our generator interconnection customer, they can easily follow the process to give us a straightforward result. And just want to highlight here, as a GFM, I think the audience probably already familiar with the GFM and GFL. So we're on to focusing on the requirement, defining the voltage source characteristic, since right now the majority of the renewable connecting to our grid mostly is GFL, which is grid following. Their operation relying on a healthy voltage profile, like a rule of thumb is if the SCR is less than 3, most of the renewable probably not gonna operation well, probably gonna see some instability. And the GFM, on the other hand, they can provide a voltage source reference to the system. And that's also the concern why this GFM become more and more important, is because with the increasing renewable penetration, all the conventional generator are leaving the grid, and there will be less and less voltage source reference in the system. GFM will become really more and more important to provide required efficient grid service to our grid. So we require simulation test to demonstrate GFM characteristics and stable control response. So just want to elaborate a little bit more on the simulation test, since we're not focusing on all these specific numbers and the values. We want to see the performance, how this GFM respond under the defined test to demonstrate the GFM characteristic, which is different, which is presenting as a voltage source, which is different from the GFL. And add a little more on this GFM requirements. What's our vision? What's the next step? So currently, the white paper defined the requirement works for the standalone battery storage. We have a lot of hybrid requirement, hybrid request, generation request in our system, in our generator interconnection queue as well. Hybrid defined is a request which include multiple fuel source. And we're also looking at the value of hardware oversizing. This we understand we've asked the oversizing, there will be additional cost included. But at the same time, the hardware oversizing, that will enhance the GFM's capability to support the grid. And the process implication, that's also very important here. Now we are connecting this standard with our generator interconnection process. So just a little background, in MISO, we have multiple process. will be benefit from this process, from this GFM standard as well. So that's the next step we're looking at. Here I want to share with you regarding the testbed we are proposing. In general, MISO's requirements will utilize the conformity simulation test to demonstrate GFM-based capabilities and performance. So the details of MISO approach aligns with the LERC white paper approach is not defining the prescriptive performance requirements. So not like the 2800, not the settling time, all this, but rather defining the core capabilities and performance. Also to be evaluated using the EMT conformity simulation test. The focus here is the voltage source characteristics. So the conformity simulation test we're proposing, mostly there's 4 tests here. The first one is loss of the last synchronous machine test. We think that's the most important core capability. Basically, this want to test once there's no synchronous machine in the system, the system still can operate because the GFM will provide the voltage reference. So that's the first test we're proposing. Under this, we have a couple sub-tests, but it's all in this category. We want to make sure the GFM, the IBR who claim a GFM can demonstrate this capability. Adding on that, we also test the low SCR with fault. So here, as you know, the SCR is a very important index for the grid following, and it's used as an indicator to measure the system strength. So it's well known the GFL normally they don't operate well once the SCR is lower than 3, which means the grid strength is not strong enough. But on the contrary, GFM they can operate at a low SCR grid, a weak grid, and can support the system. We want to test that. And phase jump is once we experience the system phase significant change, want to make sure the GFM can operate, can show the voltage source characteristic, showing the resistance of the phase jump. Rate of change of frequency is considered once there's a frequency event in the system, GFM can provide support immediately, instantaneously. And that's one of the big concerns in our grid right now, because in the past, this grid service is provided by conventional generator. It's considered there's a rotating mass in our system. Once there's a frequency event, there's kinetic energy in the rotating mass will be automatically instantaneously released to resist the frequency change, to arrest the frequency drop. And with the increase in renewable, since renewable grid following, they don't provide this instantaneous frequency support, and we're counting on the GFM to provide instantaneous frequency support similar to our conventional generator. So diving in more details about this 4 tests. The first test, the loss of last synchronous machine. We have 3 subtests for this. The first one, different scenarios is same setup. We call it test setup A because asked 3, they all have the same setup. We call that test setup B. So in the test setup A, we have a synchronous generator connected to the system. We have 2 testing the battery energy storage project. One is at the full rating 100 megawatt, another one is 50 megawatt. So here we want to add these 2 project base 100 megawatt and a duplicated base 50 megawatt. Both basically is the same inverter project we want to test. Let's say the GI generator interconnection process submit this project, utilize this inverter. So they will have to make a duplicate beds in this test bed. And we have three sub-tests. The first one is testing the best charging. The dispatch, for the first one, there's a 15% charge for the project plant, also 15% charge for the duplicate plant as well. The load will be 15% of the project plant rating. So this test will test the GFM's response once we trip off the synchronous generator. We'll see how these two projects pick up the load at the same time provide voltage reference. We're also going to see how these two projects, as they're in the charging state at the beginning, we'll see how the transition from charging to discharging and also provide a smooth transition. Same time, we want to see how this load will be distributed between these two BESS projects. The second subtest is the limit test. So here we want the duplicate plant is dispatched at 100% of their rating. The project plant will be 0%. And the load will be 100%. So here we want to see the GFM, the BESS testing, the BESS, how their performance once they're at the limit and when losing the synchronous generator. The last one is a power balance test. The project plant will be dispatched at 15%, and duplicate plant also 15%. Both projects are discharging. Plant is 75%. So here we want to see how this power are distributed after we lose the synchronous generator. There's also three additional. So it's a low short circuit ratio SCR with fault. The objective here is to verify the stable reactive current response to support voltage in weak grid areas. So in this test, we'll vary the SCRs, start from 10 and go all the way to 1.25. So 1.25 will be the grid will be very weak, and see how's the response. We want to compare the GFM and GFL response. In that way, you can demonstrate the GFM can provide voltage reference, can operate in weak grid. The phase jump test, the objective is to verify a stable active power response. So that's a little different from the low SCR test. We propose to use the 10 degrees and 25 degrees phase angle steps to test the GFM's active power response. Rate of change of frequency, the objective is verify the stable active power response as well, but since we want to test a sudden change in our frequency and see how GFM can quickly provide, can instantaneously provide frequency support. In this test, we use 4 Hz per second ramp for 1 Hz change, and test range 59 to 61 Hz. So all these 3 tests will be using the test setup B. So that's a grid connecting to our GFM testing project through an impedance. The fault will be at the almost the POI of the GFM. All these tests, simulation test, is in the EMT domain. So this slide, I want to show a little bit our example results. Sorry, I didn't make a full screen earlier. Hopefully this is clear enough. So this example is the case 1, the BSS charging. On the left, we have the example result here. So there's 2 columns here. One is the GFM and GFL. Start from the top row. That's comparing the power response. So here indicates once we lose the synchronous machine, the GFM can smoothly transition from charging state to discharging, and excuse me, and the GFL they cannot have a reference point, so they just stop operate. You see that they are tripped after the synchronous machine is offline. And second row, that shows a comparison of the react power response. Similar, we see a smooth transition in the GFM once we lose the synchronous machine, and for the GFL, again, they're tripped as well. The last row is showing the comparison for frequency and the voltage. The GFM response, they are well damped, their transition very smooth. That's what we expect to see to demonstrate the GFM's voltage source characteristic. Again, GFL, they cannot withstand this kind of event, this kind of instant in our grid. Once the last synchronous machine is out of the grid, out of service, the GFL, they just cannot operate. So this table just break down our requirement, just help our developer, our interconnection customer to perform this test to communicate with the consulting company. Just want to highlight a little bit in this LLSM success criteria for the post-trip. I can see, for example, the bullet number E, the final frequency is expected based on the droop and deadband setting. So there's a little bit calculation there. We want to make sure it's working as expected, as set. And regarding the number F, bullet number F, the oscillations is adequately damped. Also, again, here is not prescriptive. We want to demonstrate they have this expected performance, but we don't have the specific threshold numbers next to 2800. So that's our approach for our stage 1 GFM standard. Same thing for the bullet I, the react power response is immediately in the settles according to voltage droop settings. So I bring it up, just want to emphasize this language here. We are not to try to introduce confusion in our standards. More like this our intention to demonstrate the GFM is voltage characteristic. So this slide shows the example, the rate of change frequency response test. Pass them. Yeah. So here the test here is showing the GFM's response when there is a significant frequency event. So the test sequence here is the ramp of the frequency from 16 Hertz to 61 Hertz at 4 Hertz per second. Then remain at 61 Hertz for 5 seconds. Then again, we ramp down the frequency from 61 Hertz to 16 Hertz at 4 Hertz per second. Remain at 16 Hertz for 5 seconds. So we do this for the step 3 as well, just further ramp down and stay for 5 seconds and see what's the GFM response. So the plot on the right shows the example result. Top plot is GFM response, and the bottom right, that's the GFL's response. So from this plot, we can see the GFM response is instantaneously. And you can see there's a slope in the GFM response. Basically, that indicates it's a slow rate. It's mostly from the PPCs, the power plant controller as a response. And also you see there's a spike in the GFM response that indicates the inertial response provided by GFM. And it just try to, I think that's the GFM try to mimic the synchronous machine's response. So you can see a spike, then it give back the energy to the system as well. So a couple success criteria here. Want to see the plant output is well controlled with no significant frequency and voltage oscillation. So here is this example. That's we tested in one of the vendors OEM's model, we see a very smooth transition and almost flat. So there's no significant frequency and voltage oscillation. At the same time, we expect to see a voltage settles to the stable operating point when the frequency is not ramping. Again, we bring in the frequency group and deadband settings. We want to make sure that calculation is there. And so that's just in preparation for our next stage. We want to quantify all this response. Of course, we don't want to see oscillations. So the oscillations definitely should be adequately damped. This slide shows the phase jump test. The phase jump test showing once the system phase significant change, we jump 10 degrees, the GFM should provide smooth, adequate response. So the plot on the left, there's a example result. The left column, that's a GFM response, and the right column is the GFL response. In the plot, the solid blue line, light blue line, that is the first one is active power. In the dot line, that's the frequency, or that's the phase angle. So here, can see the GFM and the GFL. We don't see significant differences in the first row. Then second row, that is showing the correct direction GFM is providing to provide resistance to the phase jump event. So we can see significant response provided by GFM. Of course, from both GFM and GFL, we don't see oscillations, but we do see GFM is demonstrate a voltage source characteristic is providing resistance to system event. Here is some example plot for the short circuit ratio ramp down with fault test. So in this test, again, we're using the test B. Is the idea voltage source connecting to our testing generator inverter through impedance. The short circuit ratio, we start at 10, then just ramp down to all the way to 1.25, and also come along with a 6-cycle two-phase to ground fault. That is 0.5 pu just before each SCR transition. So it's a pretty severe situation. So the SCR transition occurs as the fault. All this happen together, and we're expecting to see the response, GFM response, the plant real or reactive power output should be well controlled, and the plant should not be tripped or reduce power for any extended period of time down to the minimum SCR in the test. We expect the GFM inverter, they can survive all this, they can operate at all these different SCR level at the same time when the system change SCR, which means we're losing a transmission element. And in a weak grid, the GFM can provide constant voltage source reference. So the plot, then on the right, there's some example results. Again, the left column, that's a GFM performance, and right column, that's a GFL response. First row is the active power, and the second one is the reactive power, and the last one is the voltage. You can see the dot line trace, that is the SCR. So just want to point out here is, I think 1, 2, 3, 4 as so approximately once the SCR drop to 1.5 to that level, the GFL just cannot operate anymore. It's 1, 2, 3, 1, 2, 3, 2. 2. The last one showing a 2. The GFL just cannot operate anymore. It's 1, 2, 3, 1, 2, 3, 2. The last one showing a 2. The GFL just cannot operate anymore. It's 1, 2, 3, 1, 2, 3, 2. The last one showing a 2. The GFL just cannot operate anymore. It's 1, 2, 3, 1, 2, 3, 2. The last one showing a 2. the GFL just start oscillating, and if once the SCR drop even lower, the GFL just start showing the weird behavior and tripped offline. I think that. But on the other side, the GFM performance shows they can operate normally under all these different SCRs and on all this SCR event. So I think that's the end of my presentation. Before I open up the question, just want to share with you a couple of references that in the appendix. This is our MISO posting. That's basically just shows recap the process. We engage the stakeholder and come up with standard. Here is a reference we were using to come up with the grid forming specifications. That's also really we are thankful for all this good reference our other industry partner posting out there make available for us. This is a couple of GFM 2800 exceptions. So just want to bring to your attention, since we do have another 2800 requirement, but since that mostly is for GFL, since GFM, their behavior is expected to resist the system performance and remain their voltage source characteristic during write-through event. So their behavior will be different than GFL in this write-through. So we put all these 28 exceptions in our white paper as well. So with that, I'm open for questions. Thank you.
Great, thank you, Weiqing.